Good afternoon, colleagues from Africa, and good morning, colleagues from the Americas. Welcome to the first Tech Talk of the second stage of the Air Quality Community of Practice. I am George Mwaniki, the head of Air Quality at WRI Africa. And on behalf of WRI Mexico and WRI Africa, I want to thank you all for your participation in this second round of exchanges of experiences among cities in the Global South. We would like to formally welcome the new members. We would also like to thank the Clean Air Fund for supporting this initiative that will now be part of the CanAIRy Alert project. We look forward to continue strengthening the capacities, sharing knowledge and learning from each other. We will start this session with an activity to find out where you are joining us from. Excellent. You can see participants from the United States, participants from Mexico. This looks like a very good representation of the global community in this webinar. And now I'm going to introduce my colleague, Christine Mothe, the Air Quality Analyst at WRI Africa, who will guide us through this session. Christine, the floor is yours.
Welcome everyone. I want to thank Anna Cecilia for the work she has done as a presenter in the first stage, and together with the Mexico team that was behind the logistics of this session. Now that the roles are reversed, Africa is now steering this, and this is my turn to represent this side of the Global South. I hope we can get to know each other and interact more. Well, this is the first session, and we want to address the air quality, data assurance, and data quality control. And our goal today here is to share with you some of the guidelines on the development of data acceptability and conformance criteria, because it is essential. And our speakers will talk about the tools that we use for data validation that produce data for simple and complex analysis. And in the first intervention, we are privileged to have Professor Gatari from the University of Nairobi, who will talk with us about what is missing in the data mining drive. With tons of experience, we are going to share his experience in the field, and we'll have the local experience session where Priscilla Adong from Makerere University will talk about the low-cost sensors. And finally, we have Russ from OpenAQ, the lead software engineer, who will address the importance of access to high-quality data for monitoring. To close the session, we'll jointly build a map or a word cloud about what is the essence of quality assurance and quality control in air quality data. We want to test your understanding of this session. So without further ado, let's get down to business with Professor Michael James Gatari, a former professor of nuclear science application from the University of Nairobi. He has a PhD in environmental science with specialization in physics, and he has a fascinating career, fascinating over 50 years, and is widely experienced in aerosol science, technology, and air quality measurement. He has authored numerous publications on air quality, and it is a pleasure not only for this community, but also to have him as a member of this community of practice, a colleague, and now our speaker. Professor, welcome.
The title is Air Quality, Data Quality Assurance and QC. There is a reason I have written that, what is missing in the data mining drive. And before I proceed, because I've introduced myself, let me acknowledge the organizers, International Science Program, and also International Atomic Energy Agency, since I wouldn't be here if they had not supported me. Now, I want to start here and start the differences. When we are talking of air quality, or rather, it has been mixed up, air quality and air pollution, in that there is studies we do for respiratory systems. There are also studies we do for climate forcing. And the initial studies in the 60s, in the 50s and 60s were on respiratory systems. Climate studies came probably in the 60s. The reason is When we are studying respiratory system, there is a mechanism of how the particulate matter, the gases, I'm going to talk about particulate matter, of how the gases go inside the system and how they reach the alveoli, where the exchange, the oxygen exchange is interfered with. Because now, when you pump in particulate matter into the atmosphere, just like the gases, you have the issue of interfering now, extra, that is non-polluted systems are okay, but when you pump in all this rubbish into the atmosphere, the earth depends on the sun, radiation, and therefore, that interference is the one we talk about climate forcing and also global warming in a way, because obviously when they go in the air, they also warm up, like the particles, they warm up, carbon dioxide warm up, and therefore the temperatures on the ground is increased. The term air quality is generalized to describe air pollution like I had mentioned. However, in the perspective of human health, the basis of air quality is criteria pollutants. And this, I know most of the community here knows, and I hope they are not getting bored with what I'm saying. And now when you come to, you cannot see CFCs here or anything like that. And when you come to climate forcing, the basis are interference of anything extra into the atmosphere above the pollutant, the natural pollutant, which the natural air as we know it. And and also criteria pollutants, organics and gases, CFCs, etc. are involved. Now remember, quality is the standard of something as measured. But now we cannot go into digging into this, whether we are right or wrong when we call everything air quality, because the scientific community, once they coin in a word, it's very difficult to disconnect. And you recall, those who have been involved in this business, that elemental carbon and black carbon had been used to mean the same thing, while they are really not the same. The properties of aerosol, but here we talk about particulate aerosol because aerosol includes gases. It depends on particle size and their concentration in suspended medium. But measurement and control particulate pollutant in the occupational and general environment require the application of this knowledge, which is basic knowledge, especially when presentations are being done in conferences. And the particle size is mainly given as an equivalent diameter so that we can discuss about a sphere. But in reality, the particles in the atmosphere are not spheres. The particle density, of course, now is the mass per unit volume. And this is what we depend on because the particles contain most of the toxic elements or components which can interfere with our health. So I wanted to bring this up, and you see, because this came up in the presentation by Kumar, by Avid Kumar, Professor on lung, he's a surgeon and a professor in Lung Care Foundation in India. And it came up in WHO in one of the workshops they called there. And you can see the healthy lung, the sick lungs, and the non-smokers' lungs. The non-smokers' lung this is from New Delhi. So you can see the kind of picture you see when you talk of air pollution in the urban environment. Now, I also wanted to bring in the quotes from Frank Fox, a moderation presentation in Kigali in January. He said, there is a lot of interest from the African colleagues, and I get probably from the South American colleagues, about personal exposures and health outcomes. This is a very difficult issue that hasn't been addressed very well in the Northern Hemisphere and just getting started in the West. And he said, I would argue we are a very long way from being able to do this well in Africa. And Frank is one of the senior scientists in well-financed laboratories in US. Now, when I come here now, I start now differentiating what I'm talking about. And I'll deal with only 3 aspects. For climate forcing, what we are doing with the low-cost monitors and everything else which is doing measurements, and the way we are doing it is okay, because we are looking at the atmosphere, even the models, the satellite data. But when it comes to human health exposure, to my own knowledge, it is not okay. Because not only are we presenting in conferences and workshops, we are not saying at what height we measured, yet we know the human being lives on the surface. Now, when you measure 10 meters, 20 meters above ground level because of safety and so forth, that's okay, because you cannot expose your instrumentation for damage of any kind from human beings or from whatever kind. But that we should always remember. We should continue doing measurements. We should continue selling our low-cost monitors data, and we should always mention to apply it in in human health exposure. It's not really up to date. Even when we do calibration, and calibration is required to be such that you do before and after, you correlate them near the next to the standard monitoring systems, which are very expensive. This is where I'm coming from. And I'll show you, I decided to bring this picture up. This was a measurement in Nairobi in 2011. And we did it, and you can see at human height level, the concentrations are by 80. This is a 11 hours measurement. And by the time you get to 17 meters, it has reduced to below 60. Now, if all this data, you converted it to 24 hours, because night time the activities are lower, you come to around 40, 60s. And that is the issue here. I have been saying, let us report the data we have, because it is not at ground level. It is not good for occupational health, but let's always mention that. Otherwise, satellite data, all these others, low-cost monitors, they will still do something. In fact, when we calibrate low-cost monitors, we are only reducing the uncertainty. And the scientific basis is optical. In reality, if you look at it in general, and it is, the science dictates that for the very small particles, you can get near accuracy. But when you come to PM 2.5, we are only reducing the uncertainty. Now, I also uploaded this up so that you can see what I'm talking about. This is measurement which is unpublished yet. And if you see the rooftop, which is 17 meters, you read 29. Take, for example, this one of February 17, you read 29 microgram per cubic meter. But when you go down to 1.5 meters, you get something in the region of 100 or 90. I can't read now, it's 87 or something. So this is what I'm talking about. And I've given data here even on black carbon. The other one is these are now the same study of 2011. You can see the kind of concentrations we got for those 11 hours. And if this data is not reduced to ground level, then obviously to 24 hours, the standard, and then ground level, it can't tell you the total expectation. And you can see it was very high in Nairobi. If you recall, in 2016, the report from the organization which actually gives data to assess the lifetime, if you come to Nairobi, you can live, they were saying it was 16 microgram per meter cubed. That means we are living in a very clean atmosphere, environment, which we really, as human being on the ground, it is not correct. Because that measurement, that data may have been corrected from our studies, which are above. The other thing I want to mention here is that particulate matter will remain a challenge, but we cannot stop measurements where the data is less. That is something we should keep in mind. But if you reason very carefully in conferences and workshops, the data is presented, this is called very good, this is a model very good, but nobody mentions at what height, very few people mention at what height they did the measurements. And it is reflected as if what is being presented also helps the exposure studies, which to me it does not. With that in mind, I just wanted to show what we are talking about when you can see this is a study done by Mutai et al. Indoors, and you can indoors and outdoors, and you can see the concentrations are all above 870. And when you come to 24-hour concentration for low cost, one of the ladies did it here, and you can see some of them are down, but they are still high, even with the low cost monitors. But the data which is reported sometimes is far much lower than even what you can get in the city. And there was some gases measurements, but we should also focus on how to do gas measurement, because that has not been very well done. And there are very few studies on this. Let the rest come from questions. Thank you very much.
Thank you very much, Professor, for such an insightful presentation. I would like to welcome Dr. Beatriz Cardenas, who will help us to address the exchange of Q&A. Beatriz, please.
Thank you so much and for this presentation, Dr. Gatari. And maybe while our participants are including their questions, may I start with one from my part. I mean, I guess you raised a very important issue, is how to present the different sets of data that we have. You mentioned that, yes, we can do, we should be reporting the data, even if we have different setups of equipment, and even we have even installed equipment in different heights, as you were showing. But we just have to say that. But I mean, we usually tend to mix all these type of data. What will be your recommendation in yes, getting data from local sensors, putting in the street level versus another in the rooftop versus a reference monitoring station at 6 meter height? How can we help the communities and the users to distinguish the different types of sets of data, but also the different type of equipment and uncertainty, how to deal with uncertainty?
Now, thank you very much, Anna. That's quite a challenging question, but the point is that to manage the uncertainty, I don't see the shortcut, because the shortcut is the only best shortcut is to the principles of measuring with the low cost monitors and the standard instrumentation for particles. And we are talking about particles now. Is a big the standard instrumentation are expensive, and that's why probably in the South we have not been able to produce so much, because even the studies I'm showing, they are short studies. So what we can do to the community is that to keep on talking, so that those who are, because the data is important for climate forcing, but those who are presenting, we hope they can also open the eyes and the ears of those who are listening that this data might not be optimum for human health, but it's okay. Because when you look at the satellite, we are talking of, now we are talking of calibration with satellite data, you know, and ground low-cost monitors. Satellite data is quorum data. Low-cost monitors have the issues of uncertainty. So the only way is continue with the calibration, give that amount of data, and then we do some studies for vertical, like the study I've shown you for 2011. In every city, if possible, we do some studies with the personal samplers, and we do vertical measurements upward. They are also, even personal samplers are not cheap, but at least one city can have one set which can do measurements on that, so that when now this data is reported, it is easy to now estimate what on the ground it is. Otherwise, it is a big challenge. And like Frank said, we are still a long way to get there. And also, when we are talking in the South, let's remember the satellites are the satellite data, and what is going on, they are well calibrated for in the North because there is a lot of luminous data. When you start applying that down in the South, we are not calibrated. And that's why you have even challenges with trajectories, you know, mining, you know, getting trajectories from the online systems. Because the terrain is different, it is not well studied, and so forth. To prevent different types of information, you have asked that. How to deal with the uncertainty. The uncertainty, to deal with the uncertainty, the only way is correlate the low-cost monitors before you go for measurements, and then bring them back. Correlate again, but remember, at the end of the day, even after all that involvement, it is just reducing the uncertainty, because the measurement, the principles of measurement are alone. The other thing is, maybe then the community, the global community can decide to change the standards of studying human health issues. But this has been studied for quite a long time. And I see no shortcut to that. Then how to describe data efficiently? Well, to describe data efficiently, you have to bring in at what height you measured so that people can know the environment. Was it in a free atmosphere, with free air flow? Was it broke? And then, have you calibrated the data? And the height is very critical. So that is, but then, when you are reporting, remember, for exposure, for human exposure, it is different. It will not be as accurate as expected.
Thank you so much.
All right, now is the time for us to have local experiences. And with us, we have Priscilla Adong, the data scientist for AirQo, an academic researcher at Makerere University, an expert in programming, research, and leadership. I have known Priscilla Adong for her work in local sensors in Africa, and she is going to give us a talk on data on ensuring the reliability of local air quality sensors in Africa. Welcome, Priscilla.
Thank you, Christine, for the introduction. Okay, yes, so local sensor calibration, but before I get into how we are ensuring the reliability of local air quality data, I'm going to give you just a brief background, just in case someone is new and doesn't really know who AirQo is. So we are an air quality monitoring project that is based at McCarry University. And we have built a network of local sensors in Uganda and across other cities in Africa. The AirQo was set up to fill the air quality data gaps. At the time, there was limited monitoring, and of course, one of the main challenges being the cost of the traditional monitoring. The reference grade monitors are very expensive, so local sensors provide like a cheaper alternative. And yes, so we have built a network, an air quality monitoring network using local sensors. They do have their own challenges, and that is where the quality assurance and quality control comes in. So our monitors are designed, assembled, and tested at our laboratory in McCarry University, and then deployed to different parts of the country. I'm going to get into the quality assurance after the introduction, so please bear with me. So once they are in the field, this data is streamed to our custom data management platform, where it's then preprocessed, stored, calibrated, and then the calibrated data is then either shared or used to build other tools, such as air quality forecasting, among others. So quality assurance. I always like to say quality assurance when it comes to air quality assurance for air quality data. You shouldn't just wait for the air quality data and then that's when you start editing with it. It should start right from the device, from the laboratory. So we have what we call the laboratory calibration. So when the devices are being assembled and complete, then they undergo certain tests to ensure that they are working correctly and they are reading the correct values before they are even taken to the field. So to do this, there are a number of tests, including, after testing, let me say the hardware, then you test the inter-sensor correlation. So each device has dual sensors. So you test the two sensors against each other and then each device against another device. These devices are also co-located with our reference monitor at one of our reference sites in McCarry University as well, before they are taken to the field. So once they have been checked for and everything is tested and we know that they are working correctly, then we send them we deploy them at the different locations of interest. So then from there, the data from the different devices is streamed through a local GSM network, that is the telecom network, to our cloud-based platform, which we use to monitor the devices and share data, etc. So the rest of the quality checks are done on this platform. So some of the checks we do before we even get to the data while on the platform are: one, monitoring the devices to ensure, first of all, they are. So when you look at the map, you can see each color means something. So is the device on? Is it off? Is it due for maintenance? And things like that, because we also would like to ensure that the data is complete, because for you to say the data is reliable, I think completeness is one of the things you should look at. So we do check, when we talk about completeness, we check the device uptime and downtime and then online status as well. So another check that we do is what we like to put, the collective term is pre-processing, but this could involve checking so we have all these tests are automated, by the way, on the platform. So you check the ranges, and then you also ensure that the devices are responding to environmental variables. There are cases where you may see if a device is reading suspicious figures, then you may need to check that device. Then finally, we do what we call the field calibration, and this is done on the devices that are deployed. So it's different from the laboratory calibration. So I'll dig deeper into the field calibration. So for field calibration, we have two permanent sites where we have reference monitors in Kampala that we use for calibration, like to test our calibration models and also develop these models. So at this site, you'll find, okay, this was a special case where we were collocating the reference monitors, but one is at let me call it site 1 and site 2. Site 1 is at Makerere University. So both of them are collocated with the low-cost devices permanently. And then we opted to use machine learning to develop our calibration method for several reasons. Of course, there are other calibration methods such as, like I think Professor mentioned this, where you bring the device, each device collocated with a reference grade monitor. But when you have a large network like we do, we have over 160 devices or even more across Africa. I can't keep pulling each and every device to Makerere University or to Nakawa, which is our second site. So machine learning gives us a way, provides a means to be able to develop a model without having to physically collocate each device. And we carried out several tests to make sure that the model that is developed using a few devices can actually work for all the other devices on the network. Yeah, so I provided a link to the paper here. Thank you, in case someone would like to have a look later. So it has all the details of the collocation and the full results. So I'm going to give you a glimpse of what's in the paper here. So before calibration, like I mentioned, we use machine learning, but before getting to machine learning, when you collocate the two devices, the low-cost sensor and then the reference monitor, which is the BAM 1022, you find that the trend is identical, but the low-cost monitor values are always higher. And it's not like a standard value where you'd say it's plus or minus 10. It varies, but it's constantly higher. And you can see that from this graph when you look at the red point. So calibration basically helps us bring these values closer to the reference grade monitor values. We tried out several machine learning models for this, and we found that random forest and lasso regression were superior for for PM2.5 and PM10 respectively, and with correlation values of up to 0.97, which is actually a very good value, because even when you collocate the two reference monitors, you still can't get a one in a way. So the tests that I talked about, the ones we carried out to ensure that this model can work in different locations and with different devices, we term these as cross-unit and cross-site validation. So with cross-unit, we tested, this is basically, when we say the unit is an AirQo monitor, a different AirQo monitor. So let me say I have 3 AirQo monitors collocated with the reference monitor at Makerere University. I'm going to use data from one low-cost monitor to develop the model, and I'm going to test this model on other devices that are collocated on the same site. Then cross-site is basically the same idea, but this time we are using the model that was developed in Makerere University to calibrate a device that is at a different location, say site 2, which is in Nakawa, for those who are familiar with Kampala. Then we did another set of tests in Addis Ababa, but in Addis, here we had access to couple air devices collocated with a BAM still. Yeah, the BAM as a reference grade monitor. And for all the tests that we did, the results were acceptable. And then the models are trained regularly to keep up with to be able to capture different environmental conditions. And then maybe one important thing I could mention is that for our models, we incorporated temperature and humidity as parameters, because we know that these are one of the main things that affect the performance of low-cost monitors. All right, so the summary of the results. We collocated, as I mentioned, we collocated the two reference monitors at the beginning of this exercise to get like a benchmark. And here I'm using our mean absolute error as the metric, the metric, but when you go to the paper, there are other metrics, including the root mean square error, correlation, and R squared. So when you collocate the two monitors, see that the mean absolute error was 4.1 and 4.0 for PM2.5 and PM10 respectively. And our model were able to achieve 4.6 and 6.0 for the two pollutants. And then for cross-site and cross-unit, this is the summary for both PM2.5 and PM10, including Addis. Maybe I will point out that the values in Addis are a bit lower than the ones in Kampala. And one of the reasons could be because the average pollution concentration in Kampala was higher than Addis for the period we considered. So in Addis, it's 22.4, and then Kampala 37.8 for PM2.5, and PM10 was about 51 point something. And in Addis, we did not have access to a reference monitor measuring PM10, so we did not test out the models for PM10 calibration. So this is the summary of the pipeline. So we have our network, the data is streamed to our cloud platform, preprocessed and stored. We calibrate hourly because this is the lowest resolution for the reference rate monitors. So when you want calibrated data, we do it, we sum up, we get the hourly average and then calibrate. And then, yes, the calibrated data is stored, and that is the one that is going to be shared with the public through our various digital platforms or used for further analysis and modeling. So one of the main challenges as we were studying the monitoring in Africa is the lack of access to a reference rate monitor. So there are several people who have set up low-cost monitoring stations, have low-cost monitors in different locations, but they do not have access to a reference monitor, and that cannot develop their own calibration models. So we have developed a freely accessible tool based on our model, where a user, if you like, you have a few monitors that you'd like calibrate the data maybe for your research, you just upload your CSV, and then you're able to download calibrated data. However, as I mentioned, you have to keep in mind that this model has been tested in Uganda, in Addis Ababa, and with AirQo devices and Purple Air. So for others, the accuracy may not be known, but we are working to include other devices as well and other locations. There are still some challenges as to why we haven't done that, and I think that is what I will conclude with. So here is basically lessons and challenges. So the first lesson that I would like to emphasize is the quality assurance should be a multi-step process. Do not wait for the final air quality data. If your device is not well tested, if it's not doing a good job, then the data you get will also not be very good. So even when you calibrate, the accuracy may be wanting. So the challenges I mentioned, lack of access to reference rate monitor is still a challenge. So we would like to test this out in other cities, but we are still working hard to get access to reference monitor data. And so far, almost none of the monitors we have had access to measure PM10. What we did for our case was, so the beta attenuation monitor can measure both PM2.5 and PM10, but not at the same time. So we were able to switch, so like between the two, but not at the same time. However, we haven't yet found a monitor that measures another monitor that is not an AirQo monitor that gives us PM10 data. Then access to meteorological data is also quite a big hindrance. As I mentioned, we need to, our devices send data frequently, like 90-minute intervals, but we calibrate hourly, right? So you'd need meteorological data hourly. However, for most providers, they will probably give you a summary for the month, which would not come in time. So that has also been a challenge. And for this, we are trying to improve our AirQo devices and incorporate these temperature and humidity sensors there to provide us with the ambient values that we require for meteorology. And then lastly, but not least, intermittent internet and power supply also affects data completeness. As I mentioned, when you talk about reliability of data, completeness should also be something to factor in. So I would like to acknowledge our sponsors and who are listed here, and thank you very much for listening.
Thank you very much, Priscilla. I really hope we have some feedback. That was very insightful to hear. And I can already see have hands up raised. So Beatrice, please take it away.
Thank you, Christine. And thank you, Priscilla, for a great presentation. Priscilla, may I start while we have some questions? I think you just mentioned something that has been mentioned sometimes, but not always recognized, like the issue of having access to calibration, reference monitoring data, so it could be collocated and then calibrated. But at the same time, we keep hearing that the equipment, reference monitor equipment are so expensive. So we have this option of local sensors. What would be your, I mean, I think just bringing the fact that we still need the reference monitoring equipment is an important one. Do you see any way of any option to bring that issue and at the same time the big possibility of local sensor network in order to have good data? And as you mentioned, like this quality assurance is a multi-process, step process, but starting with a collocation or access to reference monitoring data. Do you see any opportunities to get that message share with everyone in their quality or air pollution field?
Okay, I hope I understood your question. So yes, we are using local monitors because reference grade monitors are expensive. And in Uganda, we have, I need to cross-check, the figures keep changing because we are always deploying, but maybe above 150 local monitors. If you were to have 150 reference monitors, I wouldn't imagine the amount of money you would need for that. But so I think local monitors should help us to increase the spatial resolution of data. So we don't need reference monitors in every location. As you know, with air quality, you need like fine-grained monitoring, but we need a few monitors at least for calibration. So if I am able to have 2 or 3 monitors in a country and maybe over 100 air quality monitors, I think that would be a good use case. So at least even just maybe 2 reference monitors per country would be sufficient, at least in my view, because that is enough to develop and test the calibration models. I hope that answers your question.
Yes. And I guess just stressing that issue, Priscilla, and especially coming from AirQo with the local sensors, like it's very important. We cannot forget this calibration in order to go through the quality assurance. There is a couple of questions, and that is related also with the previous. Do you have any, in terms of the height of your local sensors network, do you have any recommendation? Do you have you set up a minimum height so you can compare, or do you have any procedures in terms of where to collocate, and in particular when you analyze the data of 2 different sensors with different height, what do you do?
The height, you mean like the level from the ground, right?
Yes. Okay,
so for our monitors are collocated, I think, about 1 meter off the ground. If I could share my screen again just briefly to show you the picture. So they are, we basically put the monitors at the height is not very different from that of a reference grade monitor. So I think the height was basically determined by the height of the reference grade monitor because we wanted to be able to sample the same air.
Thank you. And again, this is related to also the previous presentation, Dr. Gatari. If you have different, I mean, if they are located in a different height, we should say that, right? So people, when they analyze the data, they will know. There is also one question about how do you deal with inter-monitoring variation?
Inter-monitoring.
Variation, yeah. I don't know if that means that when you have different type of equipment, maybe.
Inter-monitor variation. Okay, maybe I would need more clarity on that question, but from my understanding, inter-monitor, I would assume it's different monitors, like you said. We have another study that is testing the difference between the two sensors, but at the moment we mainly deploy AirQo monitors, so they are quite similar. And we have tested our modules with only Purple Air, but hopefully we are going to check this with other monitors as well, and then maybe we can find a way of dealing with it. But right now we haven't compared, so I can't give you how we deal with it. And maybe if I'm to mention, Purple Air also uses dual sensors and the same type of sensors, which is, I think, PMS 5003. So it's quite similar with, the readings are quite similar with that of the AirQo device. Yeah.
There is also another question. It says, I have been analyzing data from Dar es Salaam city stations and found that there are data variability across different stations. How do you accommodate it when doing network-based calibration?
So data variability.
I mean, you are expecting to have variations across the spatial coverage, right? So
yeah. Okay. So I'm assuming here data variability even from the same collocation site, meaning that the devices may be collocated, but they're reading different values, not exactly the same. So like I think this takes me back to the point that I mentioned about checking the laboratory calibration. This is where laboratory calibration comes in handy. So before they are put out in the field, we calibrate, like we check all these, like are the devices reading the same values? And from our results, when you look at the paper, I think I added some plots at the end. Once they are calibrated, like when you do the laboratory calibration, and then we check the correlation to make sure like device to device correlation is greater than 0.9. So when you take them to even when they are in the field, they do have very high precision, and that is why we were able to achieve great results for cross unit and cross site validation. So basically I would recommend making sure your devices are properly calibrated in the laboratory before you take them to the field.
Thank you, Priscilla.
Thank you. Now, our final speaker of the day is the lead software engineer from OpenAQ, Russ, who has worked extensively in data management for resource management and field project. Russ leads the development and strategic direction of OpenAQ, data platform and tools. Welcome, Russ.
Thank you, Christine, and thanks everyone for joining today. All right, thank you everyone. And I'm going to talk a bit about quality assurance and quality control and how we've seen it in air quality data from the OpenAQ platform. So just to give a little bit of introduction about OpenAQ and the OpenAQ platform, at a high level, what OpenAQ does is harmonizes air quality data from around the world to get it into a single platform and into a single format so that data is more easily accessible and universally accessible from our platform. By doing this, we aggregate data from a number of different sources around the world. And this includes both government reference sites, research sites, as well as low-cost sensor providers as well. And by doing this harmonization, our goal is to make large-scale gathering of air quality data more universally accessible. Just a quick brief, we are a small team of 4 remotely distributed across the United States. We're a US-based 501c3 nonprofit organization. And then just kind of high-level statistics about the data on the OpenAQ platform. So this map kind of shows the global distribution of locations that we currently have, currently running around 50,000 locations worldwide across 150 countries. We currently have over 32 billion air quality measurements in our system. And this system is a fully open source and free platform. We have a web application as well as data APIs and other ways to download the data and make it freely available. The type of data that OpenAQ generally focuses on, we focus on the 7 core pollutants, PM2.5, PM10, sulfur dioxide, nitrogen dioxide, carbon monoxide, black carbon, and ozone. We do have other variants of some of different pollutants in smaller amounts of the data. We generally focus on these 7 though. So this is what you can expect to find. And these are the most commonly openly reported air pollutants out there too. So we kind of match what is out there. So when looking at data, air quality data, OpenAQ focuses on gathering raw measurements from data providers. There's a lot of different platforms out there that do a somewhat similar task to OpenAQ, but OpenAQ is different in that we only collect raw measurements. So we capture the raw micrograms per cubic meters or parts per million of all these different pollutants. But when you're working with this data, often if for example, you're interested in the impact on human health, usually you're trying to roll these values up, this raw data up into something that is a policy metric such as an air quality index, or again, something like the WHO's guidelines on healthy air quality. That being said, to get to these kind of indexes or these kind of thresholds that have been determined in human health, or if you're interested in climate, there's different indexes to better understand how the quality of the air in these more categorical ways. If you want to roll data up in that way, data quality and data quality assurance of that is really important because as you roll this data up, you can have a significant bias if the data is incorrect. So I'm just going to go through a couple of things that we've seen on OpenAQ, and all the charts that I'm sharing here are all freely accessible on our Explorer application, which I'll share at the end. But these are all real readings that you can find on the OpenAQ platform. So when measuring air quality data, right, there's a first place that you can find some data quality, data assurance issues is just at the instrument level. These instruments are built from different types of sensors, and these sensors, every sensor has different strengths and different weaknesses within them. So it's important to kind of know what are the physical limitations of measurement that the instruments can provide. Some instruments can only measure up to a certain level or below a certain level and have accuracy within that. Also, different instruments have different environmental sensitivities. So they can perform better at different temperatures, different relative humidities, different pressure. And some of this comes from onboard calibration against those variables. And some of that comes from just the physical nature of those instruments and how they perform in their environment. So in the chart here, this is coming from a purple air location. And as you can see, the value is very high. This is a PM 2.5 measurement of 3,300 micrograms per cubic meter, which is excessively high. I don't believe this is a valid measurement. I don't know actually this sensor and its physical ceiling of measurement, but this is an of you wouldn't necessarily want to take this data and say that the air quality at this location is really this terrible. This could likely be edited by an end user to determine if this data is actually valid. If this measurement, if this sensor can only measure up to 1,000 micrograms per cubic meter, for example, this would be a data point that you might want to check. Also, there's been a lot of interesting research. A couple of papers came out recently about the Plantower PMS 5003 optical sensors that are quite popular in a lot of low-cost sensors, and their efficacy at counting PM10. There's a lot of evidence showing that they're quite ineffective at measuring PM10. So these are important things to kind of look at when pulling the data. It's important to know the type of instrument you're working with. A more puzzling example is negative values. How can you have negative counts? How can you have negative concentrations of a pollutant? This type of data can come from uncertainty. All these instruments have a certain uncertainty built into them, and that can turn into negative values. If you have an uncertainty of 5 and your measurement in reality should be around 1 micrograms per cubic meter, you could easily fall into the negative range there. And a lot of this will come from corrections based on calibration. So the model could be overfit and could be dragging the number down. Sometimes instruments simply have errors that allow them to go into the negative values here. And you can see in the chart here, we have a negative 0.1 micrograms per cubic meter for PM 2.5. This could very possibly be overcorrection, and so it's driving this value negative. So this is one instance of a case where you would want to do some additional quality control on this, either zero this value out, remove it. It depends on the nature there, and again, it depends on the type of instrument that you're working at. I've got a link here as well to a low-cost sensor company called QuantAQ. They have a really great blog, I believe, and they have a great blog article about this exact issue of why monitors might be reporting negative values and some interesting ways about how you can work through that. Errors. So a lot of these machines can just will return error data. And a big question is, what is null? Is a null actual missing data? Is it an error? And this is really important to be able to distinguish of what your machine, what the instrument is returning. And does null mean that the machine was down? Does it mean that it was a missed measurement? Is it an error? And this can really affect data coverage. If you're creating averages, it's really important to know if you're missing data. Another very common thing that you'll see across a lot of air quality monitors across the world is a negative 999 code. And you can see this has caused an error on our system, the negative 999, and that we have this distribution plot. Negative 999 in this case is not the actual value, it's an error code. But our system has treated it as a number, and it's been rolled into these statistics, which is not correct. And so this is a case where you'd want to remove negative 999s as an error, to not include them in your roll-up statistics, because they can really skew your values, particularly if you're doing averaging, or as I had mentioned, something like an air quality index. It would be really important to remove this kind of data. And then, as I said, we have 51,000 locations that circle the globe, and air quality measurements being tied in with time. Time is a very complex attribute of data. So a great way to identify some data quality issues is to be familiar with diurnal and seasonal patterns of your locations. I really like this chart on the right, which is showing the diurnal cycle of ozone at a particular location in Turkey. And it lines up very well with what we'd expect from how ozone reacts, and in that it raises in the heat of the day and then drops in the cooling of the night. So using these cycles and knowing the environment of your locations can be a really helpful way to identify possible data problems. This chart, if it's shifted off and it's showing a peak at nighttime, you might have a time issue. So knowing the time zone of your location, and in some countries, and even within the United States, some states have daylight savings time, some don't. This can really affect and shift your data off by an hour, and can really affect the quality of the data that you're looking at. So, how can we kind of avoid and proactively improve data quality and have good quality control? And I think unfortunately, the only answer is metadata, metadata, metadata. The more metadata we have and better we understand the instruments that are collecting this data and their environment, the more insights we have into what could be an error is not an error. And we've also heard a lot about co-location. That's very helpful too. Is this location co-located with something else? That's a great way to get more information. So, the types of metadata that can be really helpful are the instrument type. What are the components that actually are taking the measurement? What is the placement? We've heard a lot about instrument height that can really affect some of the dynamics of the instruments. And how it's capturing certain sources of pollution and what meteorological effects may have on that placement. Is it in a very hot location that's collecting a lot of humidity maybe? Is it in a cool location that can affect, as I mentioned, that? So it's important to kind of know if you're trying to identify what kind of problems you might have. As I said, we like to say that we collect raw data. We collect it raw as it's reported by the entities, but a lot of these are applying a correction. So it's not raw as in the strictest form. A lot of the data has some correction applied to it, and it's really important to know, has that correction been applied? Also, the normalization of units. You'll sometimes see volume units, sometimes you'll see mass concentrations, and in between those, if it's been converted, it's important to know what constants might have been used so that you can better understand where some variability or where some data issues might have come up. And then finally, another great one that's becoming kind of an interesting topic of research is instrument age. As instruments age, there's a lot of research showing that components degrade over time, and that might affect their quality of data. And it might be really important for you to know if this is a really old unit, how much do you weight it in your analysis? So these are all different types of things, and obviously there's access to metadata is a very complicated thing, and some of this type of data is available from OpenAQ. We're working to improve this as well, because this is a very complicated topic and a lot of providers don't provide much metadata. But when doing data quality, data assurance practices, this is really an important piece to have. So like I mentioned, all these graphs come from the OpenAQ Explorer, which is an interactive web application available at explore.openaq.org. You can view all the locations across the OpenAQ network and view detailed charts about recent measurements and download data in a CSV format. So I do recommend checking that out if you're interested in learning more about data in your area. And finally, you can find OpenAQ all over the web at openaq.org. We're on Twitter. We have a Slack channel that is available, OpenAQ. Feel free to reach out on email and check out our Medium. And thank you very much. Open to any questions.
Thank you very much, Russ, for such brief yet very informative presentation that you made.
Thank you so much, Russ. And well, we also have questions from the audience. I will like to start with the metadata. You mentioned that the metadata is it's a very important part, and I guess it has been emphasized with the previous speakers that if we want to use data, we should know a lot of things about the data, how it has been generated. So based on your experience of collecting a lot of data from different data generators, what do you think that could be done in order to improve that metadata providing? Because again, from the end user, sometimes we have people who knows how to use the data. They could know that the 3,300 micrograms per cubic meter may not be real, but other end users may not know. So how can we just work with the data providers to improve the metadata? And the second part of the question is, what do you think that could be done in order to, I don't know if the word is filtering or having some quality assurance from the from your side, from before presenting that data? And now we have
so OpenAQ currently collects around data from around 100 different sources. So in our experience, it's very diverse, the amount of metadata that is available out there. I will say, although a somewhat new field, the low-cost sensor providers, I think have a a good leg up on a lot compared to a lot of reference monitoring in terms of reporting more metadata, mostly because their systems are a little more technologically advanced compared to many government systems in terms of what they're able to report. We're working to improve getting more of that, but I think what we're looking at improving, and it's something that we can work on to improve metadata is to add more instrument information. So what are the actual components? Because a lot of these data quality questions come down to that. Things like placement are difficult. We understand the general placement of things, but it was exciting to hear a lot of questions in the previous speakers about the height. That's something that's not very well reported. I think it's generally it's not as common that raw data is very well and detail reported. A lot of data is reported in the AQI space, and so I think a lot less emphasis is put on detailed data, and it's because it's difficult. This makes it very difficult to read. I mean, I think unfortunately, asking for more data quality and more metadata also increases the complexity of interpreting this data because you have to have even more data to understand it. I think we're working on building more tools to facilitate that as well. And a lot of this comes down to the needs that you need, your personal needs of the research question you might have. So it's hard to build a one-size-fits-all solution. But in addition to building, getting more metadata, we're looking at better ways to present data that on a scale that provides that richness. So it gives it a score on its richness or something along those lines, so that the user can determine better, is this something I can work with, or is it something that I know less about? Because sometimes if it's just the measurement number, that can be great. But if you don't know any context about that measurement number and you have questions about it, there's not much you can do. But if you have more metadata, we want to give a bit more of a perspective on, does this have a lot of metadata or does it have no metadata? And that will help guide users a little better to what they can do with the data. So.
And Russ, there is one question related to, you mentioned that the weather and climate conditions could affect the data. And I don't know if you want to comment. And an additional question, is OpenAQ planning to improve meteorological data that could help, to get a better idea? Yeah,
and the effect of it in our system is dependent on the location. Like I said, we have lots of different locations, and some have correction built in that might include correction from temperature, relative humidity, barometric pressure. Some don't, and so that's one case that I have seen some sources will use just a constant barometric pressure, for example, to assuming at sea level, for example, and that can be sufficient for some studies, but that might not be sufficient for your study. So that's one way that can affect things. And as I mentioned, weather can affect the components. If you look at the components and their specs, they have optimal conditions in which they run. So if it's extremely hot, and it depends on the case that they're in and how weather resistant that case might be, that can affect how the electrical signal is working and the performance of that. So those are two examples. It's kind of twofold. It's both how weather and meteorological things affect air quality as a phenomenon in the air, but also how weather affects the measurement devices. So it depends on the type of instrument. Generally, reference sensors, for example, are a bit more robust and can handle that. That's sort of how they're designed, but they're in much bigger boxes and they're much more expensive. And I think many low-cost sensors are resilient to it as well, to a certain extent. But that can affect that. In terms of OpenAQ correcting for that, we'll continue to preserve the rawness of the data. It's more that we'll try and present more information about the weather, and we are exploring getting some meteorological data that's being collected by these devices, probably not external weather data, but some devices do collect temperature, relative humidity, and barometric pressure, and that can help add that extra context. So.
Thank you, Russ.
Just a lot of questions. I never thought that this topic would spur a lot of questions and insight, because there has been so much misinformation that has been, behind what it takes to ensure that data that you work with is representative enough for the actual ground truth. Now we will just move on to the last activity. And based on what you've heard, there's been so much that has been taught today. We will build, I will call it, a cloud of key terms that we consider to be essential for data quality assurance. And there we have the question, and we'll answer this question. What is the essence of quality assurance and quality control in air quality data? We can keep the comments coming. Data validation. Amazing insights. Thank you. Great insights coming in. Kindly keep voting. We are going to see this so we can understand whether we learned. Please keep the comments coming. I can see people just saying we need to improve. The essence of air quality assurance is trust, transparency, data trustworthiness, great insights coming from all of us. Thank you so much for gracing this event and attending. I hope all of us have learned one or two concepts that we can apply in our work in air quality data. And thanks again. And we look forward to seeing you in the next Tech Talk as you continue creating this community.